We're going to finish the calculation of the Barenblatt solution to the porous medium equation. This was an illustration of the method of solving a partial differential equation by the method of scaling. So this is the, let me just remind you where we were. This is the porous medium equation. Gamma is a physical constant that is larger than 1. So gamma comes with the problem. Alpha and beta are to be chosen. We're gonna, where we got before, let's just summarize the key points. We were gonna look for a solution, a special solution V having this form. It's t to the minus alpha. U times u. U depends on x and t in the following way. U is a function of a single variable z. Z, in turn, depends on x and t in this way. Norm x divided by t to the beta. As we went along, we derived already we derived one relationship that alpha and beta must satisfy. So let's put a little box around that. And then we went on. This solution V of this solution V of this special form will solve the original porous medium equation if and only if u, the function of a single variable, if and only if u solves this ODE. Besides being second order, there's an extra, little wrinkle here. If you compare it to the heat equation, there's an extra little wrinkle here, which is that this is neither an equation in u to the gamma nor in u, right? Because you've got both derivatives of u and derivatives of u to the gamma. Let me compare to what happened when we solved the heat equation by the scaling method. Well, I should say it this way. The objective is the same. You've got a second order equation. You've got a second order equation and you want to be able to recognize this as a first order equation in disguise. That's what we did when we applied this method to the heat equation. There the issue was a little bit different. The issue was that when I say compare here, I'm reminding you what happened with the heat equation. You had something like this. A coefficient times second derivative of u. Now you've got a coefficient of this first derivative of u, and then something times u itself. You want to recognize that as a first order equation in disguise, and so you kind of grouped these two, and then you grouped these two, right? Here it's different because the issue is different. It's absolutely clear which terms are going to get grouped here. You're going to group these terms that are derivatives of differential expressions in u to the gamma, and then you got a second group over here, those that are derivatives of differential expression in u itself. Let's focus first on the terms that involve derivatives of u to the gamma. I'm talking about these last two terms, right? So if you apply a derivative, take d dz of z to a power times the first derivative of u to the gamma. Okay? Little product rule problem. So you've got the derivative of the first, leave the second one alone, plus leave the first one alone, take the derivative of the second, right? Just go down the line. Okay, and then now compare. Compare to your problem, to your problem. Look at this. Okay, right here. Look right here. Look at your term that involves the first derivative of u to the gamma. Now that's got to match up this was the ODE that we derived, right? And we're trying to express this as, we're trying to recognize this as a first order differential equation in disguise. So you're taking a first derivative here, and you're trying to match it up. And we're breaking it apart, right? First we're focusing on the terms that involve derivatives of u to the gamma. Okay, so try to match it up. Look at this term. Compare these two terms that involve the first derivative of u to the gamma, and then what you see is that you've got to make the choice delta. You've got to make the choice delta equals n minus 1. All right, and if that's the case, with that choice, if that's the case, then I'm going to factor out. I'm going to factor out z to the delta, or z to the n minus 1. All right? And here, this is my highest order term. I'm going to write it first. I write it first. So after I factor out z to the delta with the choice delta equals n minus 1, I get second derivative of u to the gamma, plus, now what happens here? What happens here? You've made the choice delta equals n minus 1. You factored out z to the delta. Sorry. Well, yeah, you factored out z to the delta. That leaves the z to the minus 1. So you've got your coefficient is n minus 1 over z times the first derivative of u to the gamma. Compare them. Compare them. This takes care of the u to the gamma terms. They match completely. Now you've got this factor, though, of z to the n minus 1 out in front, and you're going to need to be able to factor that when you, so now when you move on to the terms involving derivatives of u, you're going to have to be able to factor that same n minus 1 out. So you're going to take your first derivative. What happens when you take the first derivative of z to the n times u? And the choice z to the n was made again so that you'll be able to factor this out of the whole thing. Okay, so apply d dz to that, and here's what you get. Derivative of the first, leave the second one alone, plus leave the first one alone, take the derivative of the second. You're factoring out z to the n minus 1. You're factoring out z to the n minus 1. So here you're left with n times u. If you factor out z to the n, you're left with z times u prime. You got these coefficients of alpha and beta. But the form, right, you've got a constant times u. Right? And alpha and beta have not been chosen completely yet, so that looks pretty good. And then here, in the second term, you've got a constant times z to the u. Sorry, z times u, not z to the u, z times u prime. Okay, so now what we're going to do, we're going to take a linear combination of we're going to take a linear combination of these two terms, and then you'll get d dz. You'll get d dz of some expression equals 0, and then we'll be able to. I mean, if it all falls into place, we'll be able to solve that ODE. Okay, so we calculated what happens when you apply the first derivative to this expression. And we calculated, and then we chose our power to match up to the ODE that we're trying to solve. And we calculated what happens when you apply a derivative to this expression. And again, we made some choices trying to match up to terms that involve u and its derivatives. Okay, now I'm going to let's kind of compress a couple of steps into I'm going to kind of compress these steps into fewer steps. Or you can, again, if the more experience you have with this method, you might be able to kind of jump ahead. But here's the thing. Basically, you're gonna now, so we checked, again, we checked what happens when you apply this derivative to this. And we checked what happens when you apply this derivative, d dz, to this, right? Now what we're going to do is apply the derivative to a linear combination of those expressions. Okay, but here's the thing. A and B are both non-zero, right? Because, I mean, these terms have to be present, and these terms have to be present. So neither one of A or B is 0. And so you might as well just choose A to be 1. Or choose B to be 1, doesn't matter. Choose A to be 1, or here's another way to say it. Here's another way to say it. Constants factor out of the derivative, right? And so you can factor A out. Now you've got B over A, but that's just a constant, right? And so you might as well just say that's the same as saying A equals 1. Okay, so now I'm applying d dz to this linear combination. Again, there was no point, there was nothing to be gained by letting A and B both be unknown, right? So I'll just choose A equal 1 and leave B. But now, look ahead. Again, you can solve for B. You can solve for B. You can even solve for A and B and see that A, that's a third way to look at it. That's a third way to look at it. Just, you put A and B in there and you get the condition, you get one condition on A and B, and so one of them, is arbitrary. 3 different ways to look at the same thing. Okay, but now you can look ahead, or don't and solve for B. But here's the thing: I looked ahead. I'll look at, when I apply my derivative, look at where you get your z u prime term, right here. I match it up to my z u prime term up here in the ODE, and I see that this constant b has to be equal to beta. So that's why, so I had put that in, I had put it in as beta right from the beginning. But that was my reasoning. That's the reasoning in choosing A to be 1 and B to be equal to beta. But the point is, you're trying to choose a linear combination. You're trying to choose a linear combination in such a way that the first derivative applied to this linear combination looks like this. Okay, and it does with these choices. Now I get z to the n minus 1 factored out. I'm using what we did in the previous board. I get this, right? Z to the n minus 1 times this expression. This looks pretty good. This looks pretty good. This looks pretty good. There's only one more choice that has to be made if this, for my u term to match up. Remember, alpha and beta are still, well, beta just got chosen. Beta didn't get chosen yet. But for my u terms to match up, now alpha has to be equal to beta times n, right? So I put that, I found another condition. I found another condition relating alpha and beta. I put that over here and I put a box around it. And what you see now, and remember this was the one that we had, from one of the very first steps in this problem. Now you're in business, right? Because you've got two equations into unknowns, and you were able to solve for alpha and beta. I didn't write it down just because there's so little room on the board. But that's the point. You have found a second equation on alpha and beta, and so now you can solve for alpha and beta. And now, the original porous medium equation had a solution of that special form if and only if the porous medium equation holds. The porous medium equation holds if and only if this ODE holds. But this ODE, with the correct choices, is equal to this. So this will hold if and only if the ODE, right, is this factor. So this will hold if and only if the first derivative of this linear combination is equal to 0. ddz of this linear combination is equal to 0. The first derivative of a function is equal to 0 if and only if that function is equal to a constant. Now use your physical use the physical origins of this equation. This is the porous medium equation. It models the spread of a viscous liquid, right? U, the function u at x evaluated at the point x and the time t is maybe the height of the viscous liquid at time t and location x. For a fixed t, if x is large, u will go to 0. U will go to 0, right? And so you can choose this constant on the right-hand side to be 0. Now factor out. You've got a common factor of z to the n minus 1. Factor that out. We did this cancellation right here also. The question might have arisen in your mind, well, what if z is equal to 0? Remember that, actually we talked about this in the in-person component of the class. Remember that we are solving in a vector, in some giant function space, but at the end of the day it's a vector space. What's a vector space? At the most fundamental level, it is a set with a binary operation and a scalar operation. Binary operation on a set is a way to combine two elements of the set and get a new element of the set. These are vector spaces over the field of real numbers. If we use a complex at some point, I'll say it explicitly, but when I forget, which is almost all of the time, just assume that it's a real vector space. Okay, so your scalar operation is a way to combine take an element of the underlying field and combine it with an element of the set and produce a new element of the set. Once you get a binary operation, you can ask, do you have an identity? Does the set contain an identity for that binary operation? And we talked about this in the class. You can say that the binary, that the identity element is 0. And that's not wrong, but just be careful that when you say 0, you're not talking about the number 0. You're talking about the 0 function. And so every time we wrote the equals, I mean, be careful. Every time you wrote the equal sign in these problems, that's equality in this vector space. You're looking for these to be equal as functions. And what's here on the right-hand side, again, it's not the number 0, it's the function 0. Or another way to say it is you want this to hold for all of it, to be equal as functions means that it's equal to 0 at all values. And so there's really, including those values of z which are not 0. So if this product is equal to, the only way this product can be equal to 0 as functions is if it's this factor that is equal to 0. That's why, I mean, I'm not really canceling z. I'm saying, I'm factoring out z to the n minus 1, and then I'm saying that z to the n minus 1 times this other factor is equal to 0, the 0 function, or is identically equal to 0, if and only if it's this factor that is equal to 0. Okay, so with those two little adjustments, the choice of 0 as the constant on the right-hand side, and the factoring out of z to the n, I see that the original porous medium equation holds if and only if this ODE holds. I shouldn't really say the porous medium equation holds. There could be other solutions. I'm saying that our reasoning is a function of this really special, very highly specific form satisfies the porous medium equation if and only if the u that's in that function solves this ODE, which is true if and only if this is true, which is true if and only if finally this first order equation holds. And it's still, I mean, of course you gotta feel pretty optimistic, and now you feel like you're in business, but even this innocent looking little first order equation is not so easy because, again, it's the same issue. Well, it is greatly simplified, but you still got the same issue, really, that this is neither a differential equation in u nor in u to the gamma. Still, I mean, it is really not that hard, and we are almost there. So let's solve that first order equation. Okay, we've reduced to this ODE. So now let's solve this ODE. Even though it's just sorry, we already had an ODE. We reduced it to a first order ODE. Even though it's just a first order ODE, it will still require a few steps. Here's our equation. This is as far as we had gotten in the previous board. I want to just repeat the observation that this is neither a differential equation in u to the gamma nor in u, because both of them appear. Okay, so here's a little bit of cleverness. Again, this is the Barenblatt solution, and here's the insight that Professor Barenblatt had. And I should mention here, as I think I said this before, but I should mention that the book by Evans is a good reference for this. That's where I got this. Haven't really done anything original here. I have filled in some of the details because, again, you're asking yourself not just, can I get from this step to this step, but why are they doing this step? Why are they doing this step? And I have tried to, expand upon some of those calculations. That's all. Okay, so here's the insight of Professor Barenblatt. You're going to split off one factor of u. And when you're asking yourself, how would I have thought of that? I don't know. Maybe because you've also got a u here. So split off one factor of u and take the derivative. Now, it's the product rule. Take the derivative of the first, leave the second one alone. And that's what I've done here, except I switched the order. Take the derivative of the first, leave the second one alone, That's what I've done, but I have switched the order, so just so that I can match my terms up better. Plus, leave this first one alone, take the derivative of the second. Okay, so this gives you another way to rewrite your equation. And by the way, let me just, instead of saying it equals 0, why don't I move my beta ZU over to the other side, so it's minus beta ZU. This is the equation I'm trying to solve. Okay, so we rewrote the left-hand side. We rewrote the left-hand side by splitting off that one factor of u. And then, now I'm going to rewrite this equation here in line 1. I'm going to rewrite that equation by substituting in this for the left-hand side. So now I've got u dz of u to the gamma minus 1. And I just switched the order here too. This is this term, right? The whole thing is ddz of u to the gamma, right? But I've just rewritten my left-hand side in this way. Here's my u ddz of u to the gamma minus 1 plus u to the gamma minus 1 du dz equals, here's my right-hand side, equals minus beta zu. Okay. But here's another way to rewrite. Here's another way to rewrite this equation. You could rewrite it as gamma. Just differentiate the left. This time, just differentiate the left-hand side using, just the usual power rule and chain rule. So a different way to rewrite the equation in line 1 is just gamma u to the gamma minus 1 du dz equals, here's my right-hand side again, minus beta zu. Okay, remember that gamma was a physical constant that came with the original equation. It's larger than 1. So it's certainly not 0, there's absolutely no problem in dividing by gamma. So I divide by gamma, and I get u to the gamma minus 1 du dz is equal to this expression. And now you see that what appears here, right? This is the same as what appears here in what appears here in the left-hand side of line 4 is the same as this term that appeared here on the left-hand side in line 3. Okay, let's do just a couple more, just 1 or 2 more steps, and then we'll be ready to solve it. I forgot to say though, I had just not written it. I hadn't written it only because I didn't have room. But I recorded here in the margin on the right-hand side. I recorded my values for alpha and beta. Remember that we had obtained 2 constraints. Alpha and beta started out as constants to be chosen. We got a first relation early on, and then we added the second one. Together you can solve, and I just recorded here what are my values for alpha and beta. Remember that gamma is bigger than 1, so there's absolutely no problem here in the denominator. Okay. One more step and we'll be able to solve that equation, and then we will write down. It's amazing. It's amazing how explicit this is a nonlinear. This is a second order nonlinear PDE. We'll get a really explicit solution out. You'll see. Okay, let's solve the equation in these several steps. Again, this is the first order ODE we're trying to solve. I put that term on the right-hand side. You remember that we rewrote the left-hand side, but we split off one factor of u, and we rewrote the left-hand side, and this is what we get. The left-hand side here is a way to write d dz of u to the gamma. So equation 2 is equivalent to, is the same as equation 1. But here's another way to rewrite. Here's another way to rewrite equation 1. Just do the power rule and the chain rule. So here's another way to rewrite equation number 1. Now, sorry. Yeah. This. Okay. So now, notice that this is the same expression. This term which appears in equation number 4 is the same as the second expression that appears in equation number 3. So I'm going to substitute in minus beta over gamma zu for this term here. I'm going to substitute that in here in equation number 3. And you might feel like you're going around in circles, except be careful. And now you got to start to feel pretty good about this calculation, because these terms aren't the same. You got a beta, you've got a gamma in the denominator. Okay, so now you've got. I have rewrote here in line 3. I rewrote the equation I'm trying to solve. So now I've got u d dz of u to the gamma. This second term has been rewritten as minus beta over gamma, substituting in line 4 for this second term here in line 3. Okay, now I've got minus beta over gamma zu, and now, look. It is perfect, because there's only one term that contains a derivative, and then these have they both contain the factor zu. And by the way, I should have said, there's a second thing that's making this equation, this ODE, difficult. This first order ODE. First of all, you've got, we mentioned this already, you've got both u and u to the gamma appearing together with their derivatives. But the second thing is, this is not a constant coefficient equation. This is not a constant coefficient equation, right? Because you've got zu. And you remember, go think back to your undergraduate ODE course. You had all these methods. But the minute that you came to an equation that wasn't constant coefficient, you had to resort to series methods. Okay. So anyway, this little innocent first order ODE is not so trivial. Okay, but now we're really in business, because these both contain a factor of zu, so I reorganized, so I put them together here on the right-hand side. And in the notes, which I always want you to read, I wrote, kind of carelessly, but I think we should, be attentive to this issue. I wrote, canceling off a factor of u. Again, I want to say that you're not. Look, it's not wrong. It's not wrong to say that. In some sense, I did. Okay, you can say that, because u is not. You can cancel when the thing is not 0, when the factor is not 0. When u is not, for the function u to be 0 means for it to be identically equal to 0. What I really do is I put all my terms that involve u together, and then I factor u out, and then I got 2. So I got u times some stuff equals 0, and there are 2 ways to solve that. The first factor u can be 0, or the second factor can be 0. And by the way, because the original equation was homogeneous, but it was nonlinear, and so 0 is, not always a solution. doesn't cost you much extra work to just check quickly. If u is identically equal to 0, does that solve the equation? Yes, it does. And again, it's not a big point, but it is a nonlinear equation. You can't take it for granted. We checked it. U equals 0 is a solution. If u is not equal to 0, and that means it is not the 0 function, then this equation in line 5 will be solved when it is the other factor. Which is equal to 0. Or in other words, d dz of u to the gamma equals beta times 1 over gamma. And now I'm going to factor the 1 over gamma out and rewrite the equation this way. So d dz of u to the gamma minus 1 equals beta over gamma 1 minus gamma times z. Now it couldn't be easier. You're just going to integrate, apply the fundamental theorem of calculus, and solve for u to the gamma minus 1. Gamma is a constant that's bigger than 1. Okay, so now, for those, wait a minute, let's rewrite it. Let's rewrite this. Gamma. Gamma is bigger than 1. So before you go taking the roots, before you start taking the root, be careful, because gamma is bigger than 1, and so this factor of 1 minus gamma is negative. Just to make it look negative, which it is, instead of looking positive, which it isn't, I changed the order here. So I wrote it as C minus this. And now because gamma is bigger than 1, and you can check, remember that alpha and beta have already been chosen. They depend on n and some numbers and on gamma, all of which are, come from the original equation. Alpha and beta have been chosen, but I don't write them in every time because those expressions are, imagine, if I had put in that expression for beta, it is kind of complicated. But take a look at it. Right? It is positive. Okay, so this is a positive constant, but I rewrite it this way so that C minus this, you see the minus sign. Okay, that's it. Now, take for those values of z, for those values of z for which the right-hand side remains positive, take the root, and that gives you u, and recover. Oh, well, it should have been v, I think. V. Now recover the solution to the original. In all of your original variables. X1 through xn and t. Here's your solution to the porous medium equation. It is very, very explicit. That is the Barenblatt solution. We're going to make one further little observation about this. I just try to cram it in right here. Here's the final little observation. You will not be able to take this root unless this quantity is positive. And so you have to have I don't know. I'll just maybe say it. I'll just say it. This quantity must be positive in order to take the root. And so this has to be bigger than or equal to 0. The solution ceases to exist when this constant becomes negative. Sorry, not this constant, this function, this expression becomes negative. And look, notice the behavior for every, so you can solve this for x, for norm x. And you'll get that has to be, norm x has to be less than or equal to this constant times t to the 2 beta, you know, maybe multiply by, all of this is a constant, all of this is a constant. But what's important here is the c times 2 to the beta, t to the 2 beta. And so you see that as time, so this is the finite propagation speed. This is the finite propagation speed. And it agrees with your physical intuition. Take the cookie cutter and lift it, and the viscous liquid begins to spread. The bigger t is, as t increases, x, the distance of x from the origin can be bigger. But it cannot go beyond, but the solution ceases to exist for values of x that are so large as to make this negative. Okay, so that's the finite propagation speed. Porous medium equation also has another really interesting feature, which is, you know, you start with this cookie cutter, right? And it's got maybe some sharp edges. You lift it, and you will see that it smooths out instantaneously. Well, you won't see that it happens instantaneously. I mean, because you can't see t equals 0.00001. But you know, at least, you know, it does, you know, kind of motivate you to ask what is the regularity of the solution. You can start. Now, well, I should say this. Barenblatt solution is just an equation. It's just a solution to the actual PDE. It does not solve the initial value problem. Still, you know, you know, can give you some ideas. The initial value problem. You start with, you know, u is non-zero in some region. Maybe the region has some sharp corners, and u is 0 outside of that region. Now you lift the cookie cutter and you start the clock. You can check that for any positive t, any positive value of t, the solution u to the porous medium equation together with the initial value, the solution to the initial value problem, it will have better regularity than the initial configuration u naught, the value of u at time equals 0. Unlike, we talked about this with the heat equation, you can kind of see the infinite smoothing effect of the heat equation. Back in Unit 1, we wrote down this integral form, and we talked about how you could pass these derivatives inside the integral again and again and again, and because you've got this very strongly, you know, decreasing, you've got this e to the minus x squared term that you're integrating against. So this absorbs a lot of these derivatives, and so you end up with a solution that is actually C infinity, even if the initial value was only C0. And you do get a smoothing effect here in the porous medium equation. It's not as strong. It's not as strong. The u at a positive time t will be possess more regularity than u at time 0, but it's not going to jump, you know, all the way to being, you know, C infinity. Okay, so those are some, you know, as I said, really interesting features of the porous medium equation. The finite propagation speed, you can see it right here in the Barenblatt solution. The smoothing phenomenon takes a little more work. Maybe we'll get there later.